So let us start. So first, let me say that generally, I think I encourage people, if they feel comfortable, just leave their cameras on so Remy doesn't feel like he's just talking to me and Zlatko. So that there's other people visibly moving. Okay, so with that, Remy, can you share your screen so I start? Okay, so Remy is currently at Northumbria, which is in Newcastle, where he moved a year ago, and he will talk about, well, you can see what. So Remy, can you try to finish on the hour because some people have to leave, and then we can continue discussing it.
Yeah.
If we want, okay? So please.
Okay. Well, good afternoon. Thank you very much for giving me the opportunity to talk with you. I must say, maybe one little technical thing is that I was, for some reason, not teaching in the last weeks, in the last semester, in the current semester. So I'm not perfectly an expert with Zoom as probably most of you have become. So if there are some things, so for example, yeah, I forgot to say, so I guess that Achilles will look at the chat for me because I cannot, yeah, okay, cool. So, but with that, I will try to deliver this. And yeah, so if you have any question, feel free to interrupt me, but I should apologize if I'm not making this as fluent as everybody has become nowadays. So yeah, that's the. But okay, so after that, yeah, my name is Remy. I'm at Northumbria, as Akila said, and yeah, so thanks again for giving me the opportunity. And I would like to share with you some result we had about many-body semi-classics for Bose Hubbard systems, and in particular, I will focus on the spectral statistics and the random wave approach. I will explain what I mean, and this is joint work with Sebastian Müller from Bristol and Juan Diego Urbina and Klaus Richter from Regensburg. So I will give first motivation for what I'm going to talk about. So, and I apologize that I suspect that there are already some experts in the room, but I would like just to start with some basic things to make to make sure that we are on all the same page. So the motivation basically is that yeah, so I came from quantum chaos, and quantum chaos was for a long time dedicated with a quantum complex system. And I think it's important to distinguish between two kinds of complexity. The complexity coming from having many many interacting subparticles. And this was the original motivation of Wigner when he was talking about, when he was trying to describe the heavy nuclei. And can you see my mouse when I do that? Cool. So basically, Wigner was trying to explain the neutron scattering data. So basically, you send neutrons on a heavy nuclei. It was thorium here. And basically, you end up with investigating the spectrum of the 4,000 excited states. So very, very high in the spectrum, very, very far from the ground states. And the question is to understand this. So putting quantum numbers, trying to get the values of the quantum numbers is completely hopeless. And instead, Wigner has this idea that the Hamiltonian in certain symmetry class can be given a very minimal amount of information and modeled with a random matrix. That's how this started. So this was sort of random matrix theory, which is subsequently attached to quantum chaos, attached for complexity of many-body quantum system. So, yeah, many-body quantum system. And then there was a lot of efforts in the following decades that the same method, the same tools can be applied to system with low dimension, actually one particle. And so here is an example of a billiard system when you have one quantum particle. So you can think first about one classical particle trapped inside a domain. The shape of the domain is called a stadium. And basically the classical dynamics will be that the particle will move in straight line and reflect specularly on the boundary. And if you look at the corresponding quantum problem, you can have this kind of very, very unusual eigenstates where the eigenstate seems to follow unstable periodic orbits. And this was called scars by Harry Keller. And my personal opinion is that it's very, very different from the quantum many-body scars that was more recently introduced, but I'm happy to discuss about this later. But basically now the complexity, what I want to say is that the complexity now comes from the chaotic classical dynamics, and it induces some special structure about the quantum system. But actually people got aware that these tools, these methods can be applied to a very broad gallery of systems. So maybe a very unexpected one is to use these methods, and especially the random matrix theory approach, for number theory. I will not enter the details, but basically these are spacing distribution for some non-trivial zeros of Riemann zeta functions, so some very abstract objects. But I would like maybe more to advertise that there has been a very different type of experimental signature as well. And so quantum chaos was useful to explain the vibration modes of oscillating plates. And so here you can see that, again, some complicated structure of the wave pattern due to the vibration. Also, there was this, I think, very important experimental first measurement of Anderson localization in momentum space. This was done even before the Bose-Einstein condensate were invented. It was only ultra cold atom, if I may say, but it was the first signature. So you can see here some diffusive regime when you have some Gaussian shape of the momentum distribution, which will spread diffusively. And then here if you change the control parameter, you end up with an exponential distribution. And more recently, there has been a lot of activities actually with the microwave cavities to really check experimentally with very high level of precision these quantum chaos techniques. And I don't mention for the sake of time, but there has been several other systems like quantum dots and helium atom. But the first thing, the main thing I want to emphasize is that quantum chaos has been a set of techniques mainly for one body system in very different situation. And recently this was brought or generalized to the quantum many-body issues, quantum many-body system, sorry. And one of the main motivation is that this is at the very heart of this eigenstate thermalization hypothesis. And I'm just showing here a plot of one important result to understand it. It was formulated much before, but the idea is that if you have a quantum isolated system, despite having no bath connected to it, you can see some sort of thermalization for local observables. And yeah, one try to understand that. And the idea would be that, so is a quantum chaos relevant to that? And there has been this spacing distribution, for example, used to look at it, at least. Another object I think quite important in the recent years was the out-of-time order correlator, also known as OTOC. And it was quite surprising also that this quantum correlation function were showing exponential growth at a small time with a growth rate, which was related to some classical Lyapunov exponents. So there has been also some explanation about this. Explanation about this from my colleagues recently. But I think that, and this brings me to maybe one of the main delivery of my talk, which is that quantum chaos in general has become a quite standard tool. I mean, people heard about random matrix theory, how to use it, and but I think that the kind of more recent, at least to my opinion, and more important idea is that it's not enough to look at the spectral statistics. And if you want, for example, to do some comparison with random matrix theory, or I think that there are more questions to be raised, and looking at some the standard spectral statistics, I would say, is not enough, and especially we can do more. And this is really what I want to advertise, that coming from quantum chaos, this is really a large set of tools that we have, and I think can be relevant for many body system. And this is really what I would like to try to convince you about for today. I'm certainly not the first one to say this. There has been other works. I'm showing here some works which have been in this direction. So yeah, so if you want more references, or if you want to mention some more references, please let me know. So the goal of the talk will be a study of generic quantum many-body system. And as I said, there will be three aspects. The first one will be about spectral statistics, in a sense that, yeah, well, I'm saying that we can go beyond spectral statistics, but maybe I will first explain to you what is really, what amount of information is put in the spectral statistics. And then I will move to what we can do, what we can say about the eigenstates, and not the eigenvalue, the eigenstate of the quantum system. And I would like to finish, because I read it was a nonlinear, it was a sequence of seminars about non-equilibrium systems. So I even have a little bit of time dynamics, which hopefully can be also relevant to you. And that's it. So I will now introduce the model I have been interested. So this is the Bose Hubbard chain. Again, so I'm not exactly sure what is the background of the audience. So I will maybe, please allow me to give a short reminder. I understand this is quite standard material. So the Bose Hubbard chain is to describe n bosons on a one-dimensional lattice with L sites. And I will put on-site disorder for a reason I will mention. But basically, if you have your set of bosons on your lattice, you have two possible phenomena. Either one boson can jump from a well to the neighboring well with a cost in energy J, or if there are two bosons on the same site, there is an energy cost, which is U, and it is taken positive. So if you write this Hamiltonian in second quantized form, you introduce some bosonic operators, so which means that they are commuting, the indices are different, and when the indices are the same, the commutator of A and the commutator of A and AL dagger is equal to identity. So if you write this Hamiltonian, if you write the Hamiltonian with using this operator, so you have this first contribution coming from the hopping, the second contribution coming from the two particle interaction. And I said that I would add on-site potential, meaning that at each, so physically the idea is that the wells have not exactly all the same depth, but they may have some small fluctuation of the depth. The only purpose of this is to break translational symmetries. I will not play with disorder. I will not make it strong. So not going to many-body localization, just breaking translation symmetries. So they are independent, identically distributed random variables with a small variance. So this model has been known for a long time. The phenomenology of it, at least for the ground state properties, were probably given at least 30 decades ago, 30 years ago. 30 decades would be a bit long. 30 years ago. And then, so there is a quantum phase transition between a superfluid when U is small and the Mott insulator when J is small. And basically the control parameter is a ratio between U over J. You can add, here they had also a chemical potential for a non-constant total number of particles. But in my case, I want to keep total number of particles conserved, identical, so there is a phase transition. I will not be talking about the ground state regime. I only want to mention, to flash rapidly, that there has been an important work showing multifractality even for the ground states across the transition. So there are multifractality on both sides of the transition. I think it's kind of unexpected, and it probably has to do with the structure of the Fock space. But again, this is something which, we can later discuss.
Are you going to limit the occupancy of a single site or no?
No, in my situation, no, the single site can. I'm also considering the Fock basis states, and I will actually. It's a good point. Thank you, because I will mention them later. But I'm also considering Fock basis states when everybody is sitting on the one site. I will mention them very briefly later. So now I'm talking about spectral statistics. And spectral statistics is, as you probably know, interested in the quantum energy levels. And we are interested, the main object, I would say, is the quantum many-body level density, which I call rho of E. And in order to estimate these guys, basically, I use a certain set of coordinates in the Fock space, so which are corresponding to the eigenvectors of the creation and annihilation operators. They are not emission, so I need the right eigenvectors and the left eigenvectors. And yeah, the main first object to reach the many-body level density is the time propagator here. So the modulus square of this quantity is the probability to start at the state psi I at time equal to 0, time evolving time for time t, and then having a final state, which is described by psi f. This is the kernel, if you want, of the time evolution propagator. And the usual manipulation is to cut this evolution operator into slices, in a large number of slices, you insert the closure relation, and you can rewrite this quantity, this propagator, as a path integral. And it's a sum now. It can be seen as a sum over all the possible time evolution, which are fulfilling the initial and final condition. And so these coordinates are sometimes called Bachmann or holomorphic coordinates, representation of H bar. So maybe I want to mention something here also, because, well, for people especially coming in quantum chaos or interested, who has been interested in quantum chaos, so there has been formulation of this exact steps in a coordinate-free manner. But I think that one important character when you jump into the many-body in the many-body situation is that usually you cannot easily change the basis. I mean, the observable you are looking at is very, very much it's very, very much constraining the basis of, or the choice of the coordinates in a kind of classical canonical perspective. The choice of coordinate you are using to choose your Hamiltonian. So it's if you talk about one body system, that it's very common that you play with the coordinates, you choose the most relevant one. In the many body case, I think that for most of the, well, at least in all the situation I know, the choice of the coordinates is dictated, and that's why also these coordinates here enter the problem. So I was saying to you that this propagator is a sum of all the trajectories about the path connecting the starting and the final point. But of course, these paths have a certain weight, and the weight is given by the action. So this is something that, yeah, so if you are familiar with path integrals, something quite standard. You can see that as the Lagrangian of your system, and you integrate the Lagrangian over time to have the action, which will play a role here. And what is, I think, important is that I started, in a many-body quantum system in a second quantized form, but I'm writing here something which plays the role of a classical action. And it is a classical action, meaning that it also contains a classical Hamiltonian. And the classical Hamiltonian in this formula is given just by the average of my quantum operator into these two states. And for the Bose Hubbard system, this Hamiltonian is quite intuitive. It's just replacing the creation annihilation operator by C numbers. The second step in the semi-classical way to get the spectral statistics is to take a saddle point approximation of the path integral. So in this case, taking what sometimes is called h bar going to 0 is exactly the same after rescaling of taking n going to infinity. And so when you had this expression, you want to look at the special trajectories, which makes this action here extremal. And you end up with saddle equations, which I've written here. And basically, in the case of the Bose Hubbard, you can see that this is given by, is nothing but the discrete nonlinear Schrödinger equation, which people normally call the mean field of the quantum problem. So if you would just solve this equation, find a trajectory, and approximate your quantum problem with that, you would probably be doing what has been known as the truncated Wigner. And I want to emphasize that I'm saying something else, because you can gain a significant amount of accuracy by doing not the sum of a given solution, but taking all the solutions of your saddle equations with the boundary value conditions. You need to sum, this is a discrete sum over the path now, and you need to sum over all these paths and attribute, give them an amplitude and a certain phase, and then you gain a significant, much more accurate approximation for this propagator, and I will illustrate it further later. There are some extra phases coming in, but maybe I think I will skip it for now, if there is no urgent question. So after we have our approximate formula for the propagator, the many-body level density of states is just given by a Laplace transform through this formula. And this formula has been also evaluated within the saddle point approximation to have a consistent level of approximation. There are here some technicalities due to the zero modes, because due to the zero mode associated to the conservation of the total number of particles. I will skip this if you don't mind. And basically, we arrive at the end that the many-body density of states is given by some smooth part, which amounts to compute some volume integral, which might not be easy, but okay, there is a formula for it. And what I want to emphasize is that we can describe the fluctuation about this mean part, the smooth part, with this contribution, and all these contributions are can be computed within a mean field approach. So what I'm saying is that there is this beast that we need to compute separately. This is sometimes called also the Thomas Fermi contribution. And then there is this part when you only compute mean field approximation, what I call, because it plays the same role as a classical dynamics. And if you combine this in the following way, these quantities, I will not give you the details, but of course there are formula for them. But if you compute this formula, you get up, you obtain a description of the many-body level density, which is a purely quantum object. So in the one-body literature, this is called the Gutzwiller-Trace formula, and we could indeed check that this formula can be applied equally for this sort of this family of Bose Hubbard system. So we have generalized this quantum classical correspondence for a second quantized model, bosonic second quantized model. So you could say, okay, so we know this formula. This was checked for, it was derived for one-body system. So what's new with the many-body situation? When I think what is important is that it gives some interpretation and some intuition. And okay, the first thing is that the mean field solutions are analogous to the classical dynamics in a one-body setting. So what plays the role of the classical limit is the mean field solution when I have a Bose Hubbard system. So I think this is kind of well known. But now the thing is that we know how to go from the Gutzwiller-Trace formula to the applicability of the random matrix theory. So now we can understand, we have a criterion on the mean field solution to predict whether random matrix theory will be applicable or not. And this is what I'm showing here. I'm showing on the top the difference, how different the numerical spectral statistics for this sort of ratio, because this is the relevant in many body situation. So how this numerical quantity is different from the random matrix theory prediction. And what you can see is that, well, it is very different in the two obvious regime when U is very small and we have a superfluid, which is integrable. So no random matrix theory. This is also very different in the large J, sorry, U, yeah, so U going to 0, this is, this is the superfluid. This is also different in a large U when this is hardcore boson. And this is also where we do not expect random matrix theory, but there is an intermediate regime in the control parameter, which is there. And this intermediate regime, when random matrix theory is applicable, coincides when the mean field solutions are ergodic. And what I mean by ergodic is that you need to solve the mean field equations, which I recall here. And in the 2L dimensional phase space, see whether this solution is ergodic. And you will see that this is a criterion which is completely independent on the quantum problem, which is telling you whether random matrix theory is applicable or not.
So just to check, so we are scaling the x-axis with system size?
So you mean why there is an n here? Is that the question? Yeah. So, well, in order to make the what I've said, the derivation consistent, I said at some step that I need to rescale to have something to make the saddle point like the limit n going to infinity. And when I do that, the interaction term, which is basically the number of pairs, grows. I mean, so the hopping terms in the Hamiltonian grows linearly with n because it's only hopping, but the interaction terms grows like n squared. So if I want to have them with the same scaling with n, I need to reduce. I need to put this n in. Does that answer the question? Okay, we can maybe talk a bit later. So this was what I wanted to say about spectral statistics. So
can I ask something before you continue?
Please.
So if I understood correctly, you're saying that you solve the DNLS and then from that solution, you can do this entire thing, right? You don't need to refer to anything that is not mean field, right? So correct?
Sorry, could you just repeat?
If I understood correctly what you said, you solve the DNLS and the discrete linear Schrodinger equation, and you don't need to do anything beyond that. You just obtain stuff, calculate stuff from information you obtain there, stick it into various formulae, and you get this.
That's correct. Yes.
And you say that also that self-consistently tells you where it doesn't work, at least in this plot, by telling you that it's not ergodic.
Yes.
I mean, first of all, what do you mean ergodic here operationally for the DNLS? What do you actually look at to tell if it's ergodic or not?
So first of all, I'm looking at discrete NLS, not the continuous one. And discrete NLS, you can see as the time evolution of the vectors, which is 2L dimensional. And so it's a vector which is evolving. So NLS conserves total energy. So it's a vector which is evolving in a constant energy surface. And I'm just saying whether if I look about this super crazy object, which is high dimensional of a constant energy surface, I want to see whether a typical trajectory will just visit everything or not. If it does, then it's ergodic. If it doesn't, then random matrix theory will not work.
But do you know if random? So I guess what I have in mind, maybe it's better if I ask it later because it's tangential. As far as I remember, DNLS with disorder is actually nevertheless always ergodic.
Okay.
This may be.
Sorry.
Well, maybe let's discuss it later because I don't want to eat up your time here.
No, actually. No, but okay. There is a one there is one important fact. For this precise part, I did not put disorder here.
Yeah, so that's something. My question is tangential, and that is, would this type of thing capture something like MBL in a Bose Hubbard model with very strong U, which would be something along the lines of a spin 1/2 model? So
okay.
it's
short
tangential.
answer is that this approach doesn't work quite nicely with the disorder, because the averaging of a disorder is very difficult to implement, but maybe I can elaborate on it further later, right? So let me move to the second part. So I've just tried to remind you how the spectral statistics with using the Gutzwiller approach is a good tool to see whether a many-body system is chaotic or not, and we have some criteria about it. Now I would like to talk about the eigenvectors, not only the eigenvalues, and what can we say about it. So maybe again a short digression about the low-dimensional situation, the one-body problem. So if you take one particle inside a billiard, so here this is a quarter of a stadium, and you ask a particle, so basically you want to solve the stationary Schrödinger equation for this system, so the Hamiltonian, you want to look at the eigenvalue and eigenstates. Well, Michael Berry conjectured some time ago that if you are looking at eigenstates with a very, very large eigenvalue, very far from the ground state, then basically your eigenstates will typically look like a random superposition of solution of the problem without boundaries. So in this case, the Hamiltonian is just Laplacian, so there is only kinetic energy, but all the fun comes from the boundary condition. So here, this object is much more simple, because you take this is an eigenfunction for the free problem who doesn't know anything about the boundary condition, and you just take a random superposition of them. And what you see here is just an illustration. This can be elaborated, but what you see here is here an eigenstate of the billiard, so the true solution of this. And here this is a random wave, and black and white are corresponding to the region when the eigenstate is positive or negative. I mean, in this case, the system is time reversal invariant, so you can always have real valued eigenstates, and you see at least that the nodal region seems to have complicated but very similar structure between the two. I mean, this has been studied in more details, but just visually that there is some to give you the intuition that visually taking this sort of strange random combination of simple eigenstates is very good to reproduce the eigenstates of the initial problem. And this is what we wanted to do, what we tried to do for the Bose Hubbard system. So again, consider the stationary Schrödinger equation, and you write an eigenstates expansion in the Fock basis, and these are the occupation number in the site representation. So you have a certain number of sites, a certain number of particles. They are supposed to be large, but not infinite. And this means you have a large, but not infinite Hilbert space. It's finite dimensional. And the question is that if you expand your eigenstates, you get a sequence of coefficients. This is you can see this as the entries of the eigenstates, the coefficients of the eigenstate. And the question is that, can we, instead of looking at the true numbers for a given eigenstates, can we do some statistical description of these numbers? So can we build a statistical description of this coefficient here for eigenstates in the bulk? What I'm going to say does not apply on the edge of the spectrum. So actually this idea is exactly what was what motivates the original formulation of the eigenstate thermalization hypothesis. So first of all, what I'm going to say is fully consistent with ETH. I'm not going any step outside what ETH can say and predict. Well, if we want to do that for our specific class or model, we first need to think about applicability of the methods. Well, we need to have a quantum classical correspondence in the way I was talking before. So, and we need to have a semi-classical regime, which means that a small effective H bar, which means large number of particles in our case. Second of all, in order to apply this Berry ansatz, we need to have a chaotic classical limits. And I've just discussed that, well, we can look at the ergodicity of the mean field solution, which is equivalent also to look at the spectral statistics and how close it is to random matrix theory. And once we have this, this is our prediction. An eigenstates can be very well approximated by such a linear combination. You take all the Fock state bases, and I mean all of them, even the one which is saying that I can have all the particles on one side. And you give a statistical, you make this coefficient random with a certain distribution. Random matrix theory, which applies for the spectrum, if you apply it blindly for the eigenstates, random matrix theory, which says that these vectors have only to obey normalization condition, so there will be their distribution. Instead, what we say is that this is not the distribution of this coefficient. This coefficient have a joint Gaussian probability distribution like this. So I'm trying to emphasize that this is what RMT predicts for the eigenstates. This is what we are saying for our model from Berry's ansatz. And so this is our first statement. The second part of the statement is that from this quantum classical correspondence I was talking before, we can give an explicit formula for this covariance matrix R entering the form and entering the distribution for the coefficients. So these are kind of the main idea, and I want to elaborate about this. So, okay, first of all, this is a statement but that the whole vectors of coefficients has a Gaussian distribution, but of course, if we integrate this joint probability distribution on every variable but one, we are still getting a Gaussian distribution, but only for one coefficient now. And this is the naive way, or the kind of standard way to check. So I did some exact generalization, and now I put this order and I average over it. And I look at, for example, this regime. So this is a regime where we expect a chaotic classical limit. And you see that for eigenstates in the bulk, if I look at the overlap coefficient with this Fock state eigenbasis, I get numerically a very good agreement with the Gaussian shape. Same for different choice of Fock state basis, and especially the occupation number doesn't have to be high. I mean, surprisingly, this has one site inoccupied and still work quite nicely. So this was basically a consequence of our claim, but for a single coefficient. So we can go a bit further and looking at the higher moments of this single coefficient distribution. So if it was a Gaussian, then the false moment, okay, the even moments are zero because the mean are zero, and then all the moments are zero. But then the false moment is easy from a Gaussian prediction. And you can see that, so this is here all the Fock state coefficients. So there are more than 20,000 points. And basically, you can see that for at least half of them, the prediction for the fourth moment, which is there, and the sixth moment, which is there, is very, very good. And now I come back to the question of Latko. This discrepancy with the prediction, I personally think this is due to the fact that we are now talking about Fock states, which will be mainly occupied by eigenstates on the edge of the spectrum. And in that situation, our result does not apply. So we cannot expect that this statistical distribution can work all along. So I expect this deviation to come from the fact that we have no restriction on the choice of the Fock state basis vector of the Fock space we are taking in. And this was also seen in other model like spin chain, for example. But what is important is that after looking at the one coefficient distribution, we can look at several 2 points coefficient distribution, two coefficient distribution. And for example, the fact that it's a Gaussian induces non-trivial correlation. So if I take any 2 points, and if I say that the whole vectors as a Gaussian distribution, well, this means that there are some identities between 2-point correlator. And so here I'm showing the left-hand side of this equality dividing by the product of variance. This is the black part. On the red curve is the right-hand side of the equality. And you can see that there is a sort of quantitative agreement. It's not perfect, I agree, but it's quantitative agreement. And so maybe also I should say that this is a choice I choose in this graph. I choose N to be as detailed and M as a shorter distance with a criterion of this Hamming distance. I'm taking a Hamming distance for a bosonic Fock space, and this is basically all the states with Hamming distance 1, and some state with Hamming distance 2, for example. And you can see that still it remains reasonable, even if I take a different starting state. Okay, I can see, I guess in time is running, so maybe I will not enter this kind of, I will be a bit quicker because I would like to do the time evolution. So the last part of my claim was to say that there is also an analytical formula for the covariant matrix entering the probability distribution. So this amounts to compute this 2-point correlator function. So we start with, I mean, the people used to it will recognize some Wigner representation of the density on the constant energy surface. And basically, we can simplify this into a simpler object after some step, which I don't mean to describe, but basically what you have is this. Here, this is the correlation between two coefficients divided by the product of the variances given by our formula. And this is me who reduced the diagonal part, which should be 1, but I wanted to shrink the color range so that we can see better the background structure. So you see that this is very close. This object is very close to a delta Kronecker, which is what is expected in the thermodynamic limit. For finite dimension, this is close to, but not exactly a delta Kronecker. And there are some structure in the background. And this structure for our theory reproduces, again, quite well what is the equivalent in the numerics. This can be done for, again, another choice of the sort of basic Fock state we are talking about. This is shown here. And I wanted to say that these are, for me at least, this looks like very microscopic correlation in the Fock states. And for example, people have been looking usually at the reduced density matrix, which is a huge convolution of all the microscopic correlation I was talking before. And I think that our theory in particular is the best way to understand this finite size effect of the reduced body density matrix. Of course, reduced body density matrix will go, so I'm talking about this object now, this will go to a delta Kronecker in the thermodynamic limit. But the question is that there are deviations for finite dimension for systems which are large but not infinite. And I think that our techniques are very very powerful method in order to understand the leading term, the leading contribution of this finite size effect. So that was what I wanted to say about the eigenstates. And yeah, okay, I forgot to say, but I want to repeat that what I'm saying is fully consistent and within the parameter of eigenstate thermalization hypothesis. And I think that this brings me to the last part of my talk, which is about time dynamics. And this was a work done in collaboration with Matthias Steinhuber, student in Regensburg, and Steve Tomsovich from Pullman in Washington University. So the motivation is to go back to some old question about cell trapping, which is a dynamical transition in a sense that varying a control parameter, you will have a very different time evolution of your system. And so, yeah, this was brought up by Landau almost a century ago now. Yeah, so it was described to use it was used to describe. It was useful to describe the tunneling of a Cooper pair between two superconductors. This was also linked to the nonlinear Schrödinger equation, and more recently, it was also observed with the cold atom experiment. And I'm showing here their result in the cold atom. So basically, you have a condensate which can populate two wells, and if the interaction inside the condensate is weak, then you will have nonlinear Josephson oscillation between the population of the wells, whereas if you increase the interaction after a certain threshold, the condensate will stick to one well and will never or very rarely populate. Well, actually, in the limit, it will never visit the other wells. And so the question we are asking is that instead of two wells, what happens if we bring 4 wells, 6 wells, etc.? So my question is, what happens if we put several junctions in series? Well, not so surprisingly, this system is described by the Bose Hubbard chain, which is known to be integrable when there are two sides. And whenever you increase the number of sides, you allow for chaos in the classical limit, which for me, the classical limit is always the nonlinear Schrödinger equation, discretized Schrödinger equation. So the time evolution for the classical dynamics is this, discretized again, discretized NLS. And here is something which I think is very remarkable, is that using this quantum classical correspondence, you can also describe time dynamics, very, very large accuracy. When I was, if you remember, I was saying that you need to take your propagator and sum over all the solutions of the mean field, where this is how you get in comparison with the truncated Wigner. So here, this is a result by Steve and collaborators when he's looking at the autocorrelation function. You take an initial state, you let it evolve, and you take the overlap after some time of the evolved state with the initial one. So this is as a function of time. And basically, hopefully you can see there is a dashed black curve. The dashed black curve reproduces well the autocorrelation function at very short time and then saturate to some values. I don't know if I need to zoom in. Do I need to zoom in? I can zoom in, certainly. I can even more zoom in. Oop. So I'm talking about this graph, and you see that the black dashed line here is truncated Wigner when you take one mean field solution. Now, if you take all of them and perform the more elaborated semi-classical approximation, you get the blue one, and numerics ab initio is a red one. So you do get more information, significantly more information, when performing this semi-classical approximation. This is for 2 sets of parameters. So the idea was so the idea then is it was formulated a bit differently, in a sense that Steve was looking at the high dimensional phase space, or NLS, and he was looking at some properties of trajectories for this initial condition when side 1, 3, etc., all the odd sides are populated, and the side 2, 4, etc., all the even sides are unpopulated. And he looked at the, well, okay, let's say the Lyapunov stability coefficient, which is a good approximation of the Lyapunov exponent of this trajectory. And what you can see is that if you vary the control parameter, which is the same as I told you before, there is a certain dramatic change here when half of the Lyapunov exponent goes to 0 and the other half double their values. And so basically, you have that if you change your control parameter, half of the direction become unstable and the other half more unstable than the other half. And it can be seen as sort of trapping in this high dimensional phase space or a sort of dynamical transition. So this was seen as a classical level. My contribution was to see whether we could see some signature about it at the quantum eigenstates, and we could. So here, this is the inverse participation ratio of some wave packet associated to the initial condition. And you can see that on the Josephson oscillation side, there is a large IPR, and then it drops significantly when we cross a transition. Or you can also see it as the entanglement entropy between odd and even sites, which is high when below the threshold, and which dramatically reduces at across the value of the parameter. So we have an understanding. We are writing up the paper about it. I'm happy to discuss it further. And we got similar result. This is the result for a chain of 4 sites, but we got similar result for a chain of 6 sites, and we believe this is robust. This is time for conclusion, hopefully not too late. I've tried to explain to you how we can build a quantum to classical correspondence to be generalized for bosonic many-body system. And I think it can really give powerful prediction in the sense that looking at spectral statistics, which has become a very common tool, there is no debate about this. I think that we can improve further our understanding and also predict when random matrix theory does not apply. We can also look at the eigenstates, and we could generalize the Berry's ansatz for many-body eigenstates, and in particular, this is different and more detailed than the RMT for eigenstates, which is not enough. There has been similar result for spin chain in the largest limit. This is the chain of work. There has been several contributions by the group of Thomas Gour and Boris Gutkin. There has been also some work by Thomas Prosen and collaborators. And for the future, well, I think that this sort of approach for me is still very promising to give a quantitative understanding of thermalization within ETH and what is the range of validity of ETH, what are the fundamental ingredients about it. And another thing would be, I think, to go into infinite dimension and talk about field theory. So discussing with Achilles, I got the opportunity to advertise that we got maybe more related to the second part. We got a draft submitted this week on the archive, which is going into the Fermi pasta Ulam direction as well. And if you have some question about it, I'm happy to discuss. With that, I would like to thank you for your attention, and I'm ready for question. Thank you very much.
Thank you.
Does anybody have any questions? Otherwise, I have covered. All right, let me, okay, so I mean, just to get back to the initial bit, which I sort of understood better than this. So you have essentially a semi-classical limit, the DNLS in that case. And you say that just by solving that, you can obtain properties, you know, pertaining to the fully quantum model and for the eigenstate, for the, spectral statistics, for instance, and later. So, and you're also saying that self-consistently, this tells me when it breaks down by looking at where the classical thing becomes, the semi-classical limit becomes, the DNLS becomes non-ergodic. Now, what seems remarkable to me here is that you only need to solve a 2L dimensional problem in terms of matrices, okay, non-linear, but it's a 2L dimensional problem. And you can then tell if your system is chaotic or not. But if I had to do this for the quantum problem, I would need to solve a problem of the dimension of the Hilbert space, although linear. So I understood correctly, right?
Yes, absolutely.
Okay. Okay, there seems to be some complexity disappearing between the two, but okay. But this is just my not understanding. So okay, thinking about it, as far as I would like to find a situation where I can break, if you want, ergodicity or break chaoticity, not by integrability, but let's say by adding disorder. Now, as far as I remember from what I sort of heard about a few years ago, the DNLS with disorder is always ergodic at long, eventually. Is that?
I would suspect so as well.
Yeah.
I'm not an expert in the
me neither.
This,
okay, so
in this direction, but yeah, this is what I also.
Okay, so if what would break if I tried to do what you just did, for example, in the first part of your talk, not for the Bose Hubbard model, but for Bose Hubbard with extremely strong on-site U, so that you cannot have double occupancy, and nearest neighbor repulsion. Could I do it for that case? Just find a main field.
So let me just maybe go back to the slides so that we have.
I mean, I would still be able to find, I guess, a semiclassical.
So
rather than get that equation, I would get that. Well, actually, I don't know what would happen. I mean, I'm asking you. So if I attempted to obtain that equation, but not for the Bose Hubbard model, but for the Bose Hubbard model with extremely large U, which forbids double occupancy essentially, plus a term not nj squared like you have, but nj plus 1. Do you know or can guess?
Well, okay, so
let me tell you why I'm asking, because if you could do that, then by increasing the disorder, this is a model that's known to have MBL in the standard quantum case. If you could do this kind of thing, you would be able to find the MBL transition by solving a 12-dimensional dynamical problem to check if it's ergodic or not. Right? You see what I'm saying? I told you.
Okay, short answer is I don't know.
Yeah.
Then I know that the methods I'm using is difficult to, I should acknowledge that, it's difficult to combine with the presence of disorder, first of all. But if I try to reformulate the question, and please correct me if I'm wrong, you're asking for some classical trajectories, properties of classical trajectories when you have, so now you have this NLS, and adding disorder is just adding some epsilon L, psi L bar, psi L. So sorry, epsilon L, psi L. Sorry.
Yeah.
Yeah. So and the epsilon L are being so the question is quite different, because now you have, okay, first of all, you have a psi, yeah, so you have a random value problem. And the thing is that you want to have, so you see, the thing about the ergodicity is that the equations are fixed, and we are looking at what happens. The equations are the time evolution equations are settled once and for all. And basically the idea is to look at what happens if we change the initial condition or the boundary value problem, the initial and the end. What you're asking is fundamentally different, because you are changing the equation at each disorder. So,
but you can always say whether the phase space is predominantly chaotic or predominantly regular, right? You can, I mean, people have tried to do this for long time.
I mean, in a large U limit, you will find you will struggle to find an initial condition which will be ergodic, because large U tells you that basically you will have something very close to a well, okay, I would say I mean the equivalent of the hardcore bosons in the classical case. Yeah, but this is, I mean, I prefer to be careful here. I cannot guarantee that. I think you, okay. I think to be careful, I should say that you will not find inconsistency in using this approach, but whether this will give some predictive, non-trivial prediction for the MBL, again, the disorder thing is something a bit difficult to handle. So, sorry.
All right. Yeah. Thank you. Thank you.
That's my answer.
Can we go to your last slide? Just wanted to understand a bit better what these results were for.
Yeah, sure.
So this was, no, sorry, previous one. Okay, so here you're doing this is just the Bose Hubbard model, right? Yeah, is this for eigenstates or some dynamics or what?
Eigenstates. So now I'm looking at the eigenstates, and the question was motivated by time dynamics, but we want to do, I mean, in our paper, we would like to add some time evolution of the entropy, but I haven't been able to finish it. Yeah, so we would expect that the entropy will not have the same growth basically as a function of time, depending on which side of the transition you are. But what I'm showing here is just the inverse participation ratio of a quantum state, which is something. I mean, it's a kind of a time evolution of this initial condition.
Mm-hmm.
And you look at, so you look at the inverse participation ratio. So how many eigenstates are contributing to this time evolution, depending on the control parameter. So on one side, you have a lot of eigenstates contributing, whether on the other side, you have a few. And this is for the left plot. Now,
the state you call Z is some time evolved state from that previous configuration?
That's correct. It's a Z of
some long time or what?
Ah, sorry. So Z is the Z is the yeah. Okay, sorry. That's a very good point. So Z is the actual so it's a Wigner transform of this vector. So it's just like the states. It's the set of initial is the set of so it's the initial state which is the quantum initial state, which is the closest to this classical guy, basically.
Mm-hmm.
And because the overlap, why we are doing that? Because the overlap with any eigenstates will not change with time in the time dynamics, right? Because this is just a phase. So we look at this how this initial state, how many overlap it has with the eigenstates, so that if we know, for example, that it has a few an overlap with only a few, then the time evolution is completely different. And so this is what we see, that crossing the threshold makes the number of contributing eigenstates significantly smaller. And the right plot, thank you for giving time. I can see maybe I was too quick. So the right-hand side plot is now the entanglement entropy between these states. Yeah, so entanglement entropy between the partition of the odd state and the even state.
So you basically split into two sublattices, and then it's the entanglement between them.
Absolutely.
And there is something like volume law versus area law.
Yep. Exactly. Yep. So it's also, the thing is that as we have this quantum classical correspondence, it's kind of, for me, it's still a bit surprising that you can really play it in both ways. So we started with this classical analysis performed by Steve with this Lyapunov exponent in the large dimensional phase space. And now we ended up with some purely quantum signatures, which, just relies on this quantum classical correspondence, basically.
Any other questions? Okay, well, then maybe we can officially stop here and continue informal discussions.
Thank you.